Dear students, today again we start complex analysis. The complex analysis having a topic of complex integration. In it we have introduction part, complex integrals and their evaluation methods, line integrals in the complex plane and evaluation methods. These two main parts today we will consider. Two main reasons account for the importance of the integration in the complex plane. The practical reason is that complex integration can evaluate certain real integrals appearing in applications that are not accessible by real integral calculus. Another one, the theoretical reason is that some basic properties of analytic functions are difficult to prove by other methods. It is a striking property of this type is the existence of higher derivatives of an analytic function. In this lecture, we define and explain complex integrals, line integral in the complex plane, complex integral evaluation methods. Remaining part we will consider in next lecture. First of all, we want to define the integral in the complex plane. As in calculus, we distinguish between definite integrals and indefinite integrals or antiderivatives. An indefinite integral is a function whose derivative equals a given analytic function in a region. By inverting known as differentiation formulas, we may find many types of indefinite integrals. Complex definite integrals are called complex line integrals, and they are written as integral c f of z dz. Here the integrand f of z is integrated over a given curve c. This curve c in the complex plane is called the path of integration. We may represent c by a parametric representation as z of t is equal to x of t plus iota y of t, where t lies between a and b. We can have an example. Z of t is equal to t plus 3 iota t gives a portion or a segment of the line y equal to 3x. Another example is the function z of t is equal to 4 cos t plus 4 iota sin t, where t lies between minus pi and pi. It represents the circle mod of z is equal to 4, and so on. Now we have a general assumption, that is, all paths of integration for complex line integrals are assumed to be piecewise smooth, that is, they consist of finitely many smooth curves joined end to end. Now, existence of the complex line integral is defined as if the function f of z is continuous and c is the piecewise smooth, then complex line integral c f z dz exists. Now we have very important theorem on the behalf of line integral. Let f of z be analytic in a simply connected domain D, then there exists an analytic function f of z such that f dash z is equal to small f of z in D, and for all paths in the D joining two points z0 and z1 in D. So we have integral z0 to z1 f of z dz is equal to f of z1 minus f of z0. Now we have some examples on such kind of integrals. That is, first example we have integral from 0 to 1 plus iota z square dz. In it we integrate simply z square as z cube by 3 with upper limit, lower limit. So after putting the values of upper and lower limits, we have the result minus 2 by 3 plus 2 by 3 iota. Another example, in it we have trigonometric function cos of z with limit minus pi iota to upper limit pi iota. So as trigonometric integration, we have sine of z with upper limit pi iota, lower limit minus pi iota. On solving, we get 2 sine pi iota, and by the property of hyperbolic function, we may convert this result as 2 iota sine hyperbolic pi. Another exponential function, we have limit 8 plus pi iota to 8 minus 3 pi iota, and the function is e raised to z by 2 dz. We know that e raised to ax gives integration as 1 upon a e raised to ax. So our result is twice e raised to z by 2 with upper and lower limit. So on solving, we get the result as 0. These are some examples on it. Now we must note one interesting point, that this method is not restricted to analytic function but applies to any continuous complex functions. Now we have another theorem, that is, let C be a piecewise smooth path represented by z is equal to z of t, where t lies between a and b. Let f of z be a continuous function on C, then integration C fz dz is equal to a to b f of z of t into z dot t dt, where z dot t is equal to dz by dt, is a simple differentiation. Now we have example on it. We have to evaluate contour integration that is dz by z, where C such that mod of z is equal to 1 and counted as counter clockwise. So we may for solution, we may represent the unit circle C as z of t is equal to e raised to iota t, and t varies from 0 to 2 pi. Therefore, integral C dz upon z converted in function of t with a limit as 0 to 2 pi e raised to minus iota t with iota into e raised to iota t dt is equal to iota. With applying the limits, we have the final answer as 2 pi iota. Now we must note one point at here. Simple connectedness is essential in theorem 1. In equation 3 of theorem 1 gives 0 for any closed path, because when z1 equal to z0, so we must have f of z1 minus f of z0 is equal to 0. Now 1 upon z is not analytic at z equal to 0, but any simply connected domain containing the unit circle must contain z equal to 0. So the theorem 1 does not apply. It is not enough that 1 upon z is analytic in the annulus. We may say for the range is mod of z lies from 1 by 2 to 3 by 2, because an annulus is not simple connected. Now we have some examples on it. Integrate f of z is equal to real of z is equal to x from 0 to 1 plus 2 iota. We have the path number 1, that is along C, such that z of t is equal to t plus 2 iota t, where t lies between 0 to 1. Second part, along C dash from 0, 0 to 1, 0 and 1, 0 to 1, 2. Now we have a solution. Part 1, that is integral C real of z dz is equal to 0 to 1 t of 1 plus 2 iota dt. On solving as routine integration, we will have 1 by 2 plus iota as a part of answer. For part B, we have C dash. C dash means C1 plus C2. So we define here C1 as z of t is equal to t with the range t from 0 to 1, and C2 such that z of t is equal to 1 plus iota t with the range of t from 0 to 2. Therefore, we have integral c dash real part of z dz is equal to integral c1 real z dz plus integral c2 real z dz. So, by putting the value, we have 0 to 1 t dt plus 0 to 2 1 iota dt. So, on solving, we have 1 by 2 plus 2 iota. Note that this result differs from the result in part A. Now, we must notice at here one point that integral of non-analytic function depends on path. I want to again repeat this important result. Integral of non-analytic function depends on path. Hence, integral of f of z over the simple closed path has non-zero value. It will be noticed that again it is a non-zero value. Now we have example number 1. Evaluate integral c z bar dz and c such that right hand half of z is equal to 2 e raised to iota theta with the range of theta is minus pi by 2 to pi by 2. So, on solving, we have z as e raised to iota theta with 2 times. So, we converted z bar with the negative sign, and after integration with limit from minus pi by 2 to pi by 2, on solving we will get result as 4 pi iota. Another result is evaluate integral c root z dz where c denote the semicircular path z equal to 3 times e raised to iota theta and theta lies from 0 to pi from point z equal to 3 to the point z equal to minus 3. At here we have root z, so we convert z raised to power half with the value of z and we differentiate to obtain the value of dz with limit of integration, and after solving we get the result very easily minus 2 times root 3 with 1 plus iota. It is the example of path of integration, and later soon we continue the chapter with remaining parts like Cauchy integral formula, Cauchy theorems, and with some examples. Thank you.